Welcome, I should say. I think everyone can hear me well. And I'd like to welcome you at our fourth AIRTuB deliverables meeting. And this time we have this meeting at entrance in Groningen, facilitated by Hanzehogeschool. And we are very pleased that they were willing to do this. And of course, the reason for this is that Hanzehogeschool is in the lead of work package 6, which makes an important part of, let's say, the AIRTuB project, and which results will be presented here at this meeting. Also welcome to our online attendees. I don't know how many there are, but I hope there are some. Well, as you can see, we are not with too big an audience here, but anyhow, enough to share the results of let's say, the work packages 6, 4, and 7 of the AIRTuB project, which will be, let's say, end of this year after 3.5 years of research and development. I put on the screen, let's say, the erosion modeling and repair recipe as more or less the name of this of the topic of the meeting. But of course, this comprises the results of, as I told you already, work package 4 and 7 and 6. Maybe a strange order, but 4 and 7 are combined and 6 is separate. And before we go to, let's say, the contents and the presenters of this afternoon, well, I think it's good to have a look at the program. As you can see on the screen, we will have well, several presenters before the pause and after the pause. So, and then in the end, we hope that we can have also a kind of panel discussion. We have to see how, let's say, how to operate this, but I think it's good to have some discussion afterwards. But first, we have to, let's say, listen and reflect on the presentations that will be given here. I'm not sure, I don't think I mentioned I introduced myself already. For those who don't know me yet, that is still possible, of course. My name is Ferry Visser. I'm program manager of Field Lab Zephyros, and I am also the general project manager of the AIRTuB project, which is the biggest project within Field Lab Zephyros up to now. Well, I think that's good for the program for now. And before we go to, let's say, the presenters, I'd like to share with you well, maybe for the ones who don't remember well, what was the reason to start up the AIRTuB project. When we started this, and this is a slide I found from the start meeting of the AIRTuB project, so more than 3 years ago at Skalda in Vlissingen. There we had the starting meeting, and then we showed this slide where we mentioned that we have the ambition to increase the annual energy production of offshore wind farms. We have the ambition to decrease the cost of operator maintenance, and we have the ambition to decrease the, let's say, number of man-hours offshore. And during the last, well, during the project, this last topic has become more and more important, as we are faced with real challenges in available people to do the maintenance, and also challenges to do the maintenance, let's say, in a proper way, while it is very often not possible to visit the wind farms. So I think these ambitions of AIRTuB are very relevant, are still relevant, and with our project we hope to contribute slightly to that. Here you see an overview of the whole, let's say, work package structure of the AIRTuB project. For the ones that were not involved in the project, maybe it's good to have this this overview. As I already told you, this afternoon we are discussing the results of work package 4, 7, and 6. And 4 and 7 are that's more or less a combined work package. It has become a combined work package. Well, if we consider work package 6, this is also a slide from the startup presentation. this was about erosion modeling and repair strategies. And there was a goal to model and validate an aerodynamic effect of erosion on power production so that loss from erosion can be balanced against the cost of erosion repairs. Well, we hope to hear more about this in the upcoming presentations, of course. And then I must admit, I forgot to put here the goal of work package 4 and 7, but these goals are, let's say, related to this, of course, and I'm sure the presenters of work package 4 and 7 will tell us about that in their part of this meeting later on this afternoon. Of course, as I already told you, the ambition of Field Lab Zephyros is, it used to be zero downtime and zero on-site maintenance in offshore wind, but it's developed towards unmanned maintenance. That is what we are aiming for, and we got rather convinced that if we realize unmanned maintenance, let's say the downtime ambition will be served as well, because that will, in the end, also create less downtime in the wind farms if we have the repair and inspection facilities on site all the time. I'm not sure if people know world-class maintenance, because Field Lab Zephyros is a world-class maintenance initiative, and maybe this gives a brief overview of what world-class maintenance is. It's the Dutch network for smart maintenance, as we always say, and world-class maintenance operates projects in all different sectors of industry and infrastructure, all from the perspective of developing smart maintenance. And as you can see here, it's also a member organization, so there are many members, let's say, involved in world-class maintenance, and also members of the Zephyros program are members of world-class maintenance. And world-class maintenance has several innovation programs and innovation projects, and specifically there are a lot of innovation field labs. And well, the specific characteristic of a field lab is that there is physical testing, developing, and prototyping in the project, which we have within AIRTuB as well, as you know. Of course, we collaborate with several other companies, and as you can see here, the NNOW is one of our partners, and we are here in the north, and well, of course, then it's good to know that we are linked to the Northern Netherlands offshore wind community, and also to the Offshore Wind Innovation Centrum, which is also, let's say, founded here in Groningen. Then in Vlissingen, we do have our own test development and, let's say, demonstration site, which we call the Kaap. And there we have several pieces of equipment that can be used for serving learning and innovating, because there we combine learning and innovating. This is an overview of, let's say, maintenance robotics in offshore wind, and AIRTuB is, let's say, our project in this field of business. And as you can see, there are many partners in maintenance robotics in offshore wind that we work together with, and the majority of them are also involved in the AIRTuB project. The AIRTuB roadmap may be good to, let's say, to realize that we are not there yet. We have been researching and developing for the past 3 years, and that means that we are more or less at the end of the first phase of AIRTuB, and we are working on the development of the next phase, which will be AIRTuB 2. And in AIRTuB 2, we will, we have the ambition to work on further developing the, let's say, inspection methodology. Also, for instance, lightning damage inspection, which is apparently rather relevant. But besides that, we want to work on the residence of the inspection robots in the wind farm as well. So that is a new project which is being developed at this moment, and which we'd like to start up next year. Well, here is a brief overview of other projects that we are working in within Field Lab Zephyros, but I think it's not necessary to explain this furthermore now. And this is more or less an overview of what Field Lab Zephyros has to offer to, let's say, to industry, to parties that want to innovate and parties that want to be active in offshore wind. That's more or less my introduction to this afternoon. And I think it's time to hand over to the first, let's say, content presenter of this afternoon. So I'd like to ask Gerard to come to the stage and take over from me. And I think, well, now it becomes interesting.
Also very
Here you are.
very kind introduction. I hope everyone can hear me, that also the people who are attending online can hear me, that this microphone works. Let me see, thank you, Ferry. The presentation, can it be put on the screen? Yes, that's the presentation. So yeah, well, welcome everybody. Yeah, my name is Gerard Schepers, and you see that I have two positions. I work at the TNO Energy Transition, the former ECN, Energy Research Center of the Netherlands. But yes, I also work here at Hanze University of Applied Science. And I was also the leader of this work package 6, erosion modeling and repair recipes. And before I give the floor to the main presenters of this work package, I dare to say, and that is my colleague Kishore from TNO and Loek from Hogeschool Zeeland, I will give a short overview of what work package 6 did. And I will also touch upon a few activities which are not presented by Kishore and Loek, so I will do them. But here you see the participants, yeah, TNO Energy Transition, Hanze, Hogeschool Zeeland, and also NLR, the Dutch Aerospace Laboratory. And the goal of work package 6, the overall goal was already presented by Ferry, but here you see it a bit more specific, is to answer the question, how can we model the aerodynamic loss from a given blade erosion, and what is then the resulting loss in wind turbine energy production? On that work, some activities had already been done by other partners. I myself like these results a lot because they were done by an industry and they come from a European Union project which I coordinated. That was the AVATAR project on wind turbine aerodynamics. And the industry was LM Wind Power, the large blade manufacturer. And within AVATAR, they said erosion is so important that we want to invest on that with wind tunnel measurements. And what you see here is the power curve for clean and eroded blades, but also on the right side, the loss in energy production, which then varies between, say, 0.5% and 2%, dependent on the wind climate. But much more important, at least to my point of view, than these exact numbers is the fact that there is not a unique answer to this question. It depends on so many things. It depends on the turbine, it depends on the control, it depends on the wind climate, as you can see here. It of course depends on the erosion. So the fact that there is not a unique answer means that we can only find the answer by tools. And that is the goal of this work package, to find these tools, but not alone. We also have a goal to classify and that is work from Loek, to classify an arbitrary blade erosion into different categories and to develop a repair strategy for different erosion classes and implement it into a decision tool, which then gives us the following sub-work packages. Yeah, I call work package 6.1 aerodynamics, and that will later be presented by Kishore. And then work package 6.2 is the classification of erosion, which will be presented by Loek. And then we also have a guest presentation from Beatriz Mendez Lopez, from Spain, from beautiful Pamplona. She will present online, and I consider her as a real expert on erosion modeling and she will present the activities which she is doing at CENER, which is a kind of ECN, but then in Spain, so an energy research laboratory. But before I give the floor to Kishore, Loek, and Beatriz, I will first explain the general procedure to determine the energy loss. And in that procedure, we make use of the so-called blade element momentum theory, the BEM theory, which means that you divide the blade in a number of elements, and every element has an airfoil, a cross-section with a particular shape. We call that an airfoil shape. Thick airfoils at the inner part of the blade, thin airfoils at the outer part of the blade, and the aerodynamic forces on these airfoils, they are given by a so-called lift and drag coefficient, CL and CD, which are given as function of angle of attack alpha. And usually that's given by wind tunnel measurements. You see here wind tunnel measurements from TU Delft. But that part is, we will not talk much about it because that's very standard, such a BEM theory. We sometimes even ask students to make their own BEM method, and they can do that very easily. The challenge lies in the determination of this reduction in lift coefficient, the reduction in CL, and the increase in drag coefficient, the increase in CD from erosion. And for that, we tried 3 different approaches. The first one is what we call a lower fidelity, so a bit more global, with more assumptions, less accurate, but very fast. An engineering approach where we use a program which is called airfoil, and a generalized erosion. But, and that will be presented by Kishore, we also use higher fidelity, so more accurate, much more advanced CFD, computational fluid dynamics. And therefore, Kishore used 2 approaches, one with a generalized erosion, and one, and for me that was always the point on the horizon, but Kishore made it happen. He also used the actual scanned 3D blade geometry into this CFD approach. So that will all be presented by Kishore. I have 2 slides about this airfoil approach, which actually is an extension of an approach from Sandia Laboratory in the United States, but they relied on the publicly available X-foil code. That's an airfoil design code from Aeronautics, and they calibrated their approach with 1 set of wind tunnel measurements. We used airfoil, which is an extension of X-foil, but made suitable for wind turbines. Was developed in the 1990s already by ECN, so TNO, but at that time ECN, TU Delft and NLR. That version is publicly available. Later some updates from TNO, they require some negotiation. But we also used more measurements for calibration, and they were again provided by Sandia in the United States, so we're very grateful to them. But this approach assumes that the aerodynamic effects of erosion are determined by the forward shift of the boundary layer transition point. And what is that? That means the boundary layer transition point, that is the point where the boundary layer, the thin layer around a subject, changes from a laminar flow, a smooth flow, to a turbulent flow, a more chaotic flow, and that leads to an increase in drag, and that transition point moves forward when you have erosion. And that forward shift is then in this procedure calculated from a so-called IK, which is a very complicated function, but at the end it boils down to the height and the density of the roughness element. So it's a measure for the roughness, and then an F, which is a function of this IK. And let me see, yeah, that F, if that F is 1, and you see that happening here for small values of the IK, for small roughness, then there is no shift, no aerodynamic effect of erosion. But if the IK becomes larger, if there's more roughness, the F becomes smaller than 1, and then we do have that forward shift. And these curves, they are calibrated with wind tunnel measurements. Yeah, so it's all about the transition from laminar to turbulent flow. This comes from my colleague Rogier Nijssen. He's a professor in Holland, but he doesn't like, he's on composites, and he doesn't like aerodynamics so very much. And he said to me, oh, when you talk about laminar flow, I always thought you meant a lamp in a flow. But then I said, no, a lamp in a flow is really something different. A laminar flow means a smooth flow. Turbulent flow means a more chaotic flow. And that transition is a main driving parameter when we talk about erosion. And just to finish, here you see some results from that approach. What you see here are absolute differences between that airfoil approach and these Sandia measurements. And you see there a difference in CL, absolute difference in CL, absolute difference in CD, and the difference in transition, boundary layer transition point. Then you do see some differences, definitely. But many of these differences, you see it for clean and rough conditions, eroded conditions, are already there for clean conditions as well. But you also see a spread in result. And that spread in result is a result from the different calibration curves. So it matters which calibration curve you take. That's why we said we also want to do our own wind tunnel measurements. That was done by NLR in the Dutch Aerospace Laboratory in their LST wind tunnel. And they did measurements on a DU, airfoil from the University of Delft, DU-21. It was very extensively measured in that EU project Avatar, which I mentioned before, but then mainly for clean conditions. But here we sprayed grain directly on the airfoil instead of using sandpaper to simulate roughness, because that is often done using sandpaper. Beatriz may also talk about that. She also knows about that. We wanted to grain this directly on the airfoil because sandpaper also has some backing paper at the backside of the sandpaper, which also gives an unknown roughness. So here it was sprayed directly on the airfoil. I still think that's a good idea. The only thing is the clean results already differed from this known clean performance which we measured in Avatar. And we spent a lot of effort in trying to find the explanation. Everything indicates that there is some premature transition, that there should be something with a deviation of the airfoil shape or maybe some roughness, despite the fact that it should be clean. NLR scanned the airfoil. We put that into our 2D codes and we saw that it partly explained the differences, but not completely. We also saw some 3D shape deviations, but yeah, we didn't have the resources to do a full 3D CFD calculations, but that could then be the explanation. Despite this, we reported all the lessons from this experiment, and I still think they can be useful in follow-up experiments. We learned a lot from it. Yeah, and one of the things we learn, and that's a bit, I always emphasize this, is the Reynolds number. And what is the Reynolds number? Well, it's a kind of aerodynamic scaling parameter, very important when you do wind tunnel measurements and you want to compare it with field measurements. Then the Reynolds number should be similar. And it's determined by size, velocity, and viscosity. And this boundary layer transition, remember this change from laminar to turbulent, depends heavily on the Reynolds number. I said these erosion effects are largely determined by transition, so that then indicates to me that the erosion effects are also largely determined by the Reynolds number. But then, because these offshore wind turbines are so big, the Reynolds number can easily be above 10 million. Yesterday I was in a discussion with LM Glass Fiber, or LM Wind Power as they are called nowadays. There we found that the Reynolds numbers were even 14 million, where wind tunnel measurements, conventional wind tunnel measurements, because the size of these wind tunnels is so small, well, I say here 6 million, but very often it's not more than 4 million, so it's much lower. There's one example, maybe a few more, but again in this Avatar project where we used a special wind tunnel, a pressurized wind tunnel, and there we could reach a Reynolds number of 15 million. And we found then that X-foil or R-foil can predict this airfoil performance at these high Reynolds number well, where CFD was predicting poorly. That's strange because X-foil I mentioned to be a low fidelity and CFD is high fidelity. But it's not so much X-foil versus CFD, it's more, again, this boundary layer transition model for which X-foil uses a so-called E to the N method, which, by the way, is developed by my old professor Van Inge from TU Delft Aerospace. I graduated with him in 1986. He's still a bit active, so he developed a wonderful model because it works very well, where CFD was using and Kishore will talk about that, the so-called SST-LM method, which was not working well for high Reynolds numbers. But when CFD was using this E to the N method, it was also much better. Or, and that was done by my colleague Marco Carboni, yeah, there he is. You can change this SST-LM model to make it suitable for higher Reynolds numbers. So I want to give the floor now to the other speakers. I want to conclude with saying that this R-foil approach can be used to determine the aerodynamic losses. It does need such a generalized IK. You need to define that from erosion patterns that may need some experience. And yet this calibration curve should be taken for a situation as representative as possible. Same airfoil preferably, same Reynolds number, as close as possible, the better it is. Or you use CFD, and that is presented by Kishore. Yeah, and my thing is, I keep on saying we need to do more on erosion effects, on high Reynolds numbers, because the Reynolds numbers on offshore wind turbines, they are high, and there the aerodynamics is different. We made a summary report of this work package 6.1, so that will be published. Yeah, and here you see the list of deliverables from work package 6.1. Also quite some student work. Janos was a student from Hanze working at TNO. Joshua was a student from in Holland. So that is all publicly available. And I want to finish with acknowledgement to the TKI for funding this project. Definitely also Sandia for the wind tunnel measurements. It's publicly available, but David Maniaci already supplied the measurements before they made it in a public database. Yeah, and of course, Ferry and Jeroen for the wonderful coordination. Well, I understand Jeroen is in Cambodia, but maybe he will listen in. I think that's it.
Yes. But before we switch over to Kishore, are there questions? I know this is quite scientific, what you told. There might be some questions from the audience. So is there anyone who has a question for Gerard? Anyone online, but I don't know if we can see that. That will be a little difficult. And yeah, well, I have a question.
Yeah.
Are you satisfied with the results up to this point within AIRTuB?
more than satisfied. I think we have really good tools now to model erosion. We have much more confidence in it than we had before. Well, there is, of course, I mentioned some subjects which need further research,
Definitely.
but yeah, I'm satisfied.
So I
also
think
students, we had students in our project. That's always also important for me. These students have learned a lot from it.
of course.
Yeah,
So we add value to, let's
For
say, the
me,
development of wind industry.
I find, yeah, I think so.
Well, I think that then I am satisfied as well as a project manager. So thanks for your presentation. And I think we are going to listen to Kishore. Kishore, the floor is yours. And you can use a hand microphone if you like, or you can use this one as well.
Okay.
The green is, I think the presentation will be shown now.
Right.
And green is forwards, red is backwards.
Great. Thank you.
Yeah, okay.
Thank you very much, Gerard, for nice, kind words on our work. I must credit our work also to my colleagues at TNO. Harold Meyer, he's also in the audience today. And we have Jana, who also worked on it, including Gerard with this research topic on modeling erosion for wind turbine blades. So, welcome everyone. My name is Kishore from Vimalakanthan. I work at TNO as an aerodynamic researcher, mainly looking at tools for numerical modeling aspects and performing validation around them, try to establish tools that we can use for predicting performances, etc. So today, I will be presenting some of the work that we did within AIRTuB, particularly on tools that we can emphasize the aspect of erosion to a wider audience and why it's necessary that erosion is a problematic area for wind turbine for the future also. Yeah. Yeah, that's fine. Sure. Hello? Does it work? Okay, great. So I think there will be a lot of aerodynamic jargon here. I hope I don't do much for boring a presentation here, but I'll try to make somewhat an explanation on the physical scenarios. But generally speaking, erosion happens at the tip part of the blade. And tip part of the blade is what contributes most of the power production. And it's also where high flow velocities happen because of the rotation. So it's the crucial part of the blade that generates power production. And that's the part where erosion happens. And in order to get better performance output from a turbine of the future, we need to be able to model such cases to get some predictability around it and design some sort of robust designs for the future. So the main topic here is the modeling aspects. And the presentation is divided into two parts. The first part, I will focus on what Gerard kindly described, the transition process and how we can model transition within CFD. But the novel part is here we will add the effect of erosion with the order of roughnesses levels and be able to model transition including the effect of erosion with roughness elements at the leading edge. So that's the first part. The second part, which is much more interesting for us because my colleague Harold went into the field and was able to scan an eroded blade and came back to TNO, and we were able to translate that to within a CFD environment and actually model that in a 3D flow environment to calculate the effect of erosion in that way. So we're very excited to present that part here as well. But in general, what Gerard mentioned about how we calculate the performance is that we evaluate sectional performances using CFD, and then we supply that differences to an BEM code to determine the losses in AEP values. Okay, let's get to the CFD part. So now the first part, like I said, I will talk more about the transition modeling. Bear with me, there's quite a bit of technicality involved here, but I will try to make it easy as possible for those who might not favor these kind of presentations, but okay, here goes. So, in the past, it's been decades of research into transition, and within CFD environment, we have numerous authors have developed models to model transition, and one of them that I will be using here, it's developed by Mentor and Langtree, hence the name SST-LM. LM stands for Langtree-Mentor, and the SST model, it's also developed by Mentor himself, and that is basically used, the abbreviation goes as shear stress transport. But what it means is this: there are so many variety of transition turbulence models that we use to predict the flow around aerofoil or any aerodynamic surfaces. And this particular model gives us the capability to predict performances under naturally transitioning flow. So it will calculate performances incorporating laminar flow as well as accounting for the triggering to turbulent flow. What's more interesting about this work is that we added the account for the roughness at the leading edge. That is approximated by erosion levels at the leading edge. So this model was actually developed in the 2012 by, actually was proposed, and later on it was developed in 2017 by Langhal, who developed it for Overflow 2 solver, but we at TNO have developed it within open form now to be able to model transitioning flow with roughness. Yes, here are the equations to be able to model this transitioning flow. In general, what I have here is that we have some transport equation. Within the numerical simulation, we will transport a variable that acts like a trigger to tell the flow to, okay, because of roughness, we have some amplification on the boundary layer transitioning process, so transition earlier. So that's the physics behind the physical aspects behind it. And with these fancy equations, we can actually do that and add the effect of roughness with this Ks value, which is a measurable quantity, in fact. So I will, later on, we have a publication on this. If you want more details, please, I would like to refer to that. But let's get to the results. So here, I have a plot of lift curve on the left top corner, and then on the right-hand top corner, the drag curve. And the symbols shows the CFD results, and the lines are representing the experimental results. And if you look at the left bottom corner, we have a coordinate of the section with the region where we applied this roughness to basically mimic the experiments that was done at Sandia. What I want to highlight here is these red symbols on the top right corner is the drag curve, red symbols with the red line. It shows that this model was able to predict the drag increase due to having rough leading edge. And predicting drag with CFD is quite a task. And I was really impressed that we were able to capture this detail to be able to catch this increase in drag. On the other hand, we also see on the right bottom hand corner is these transition locations. And we can see that the model and the experiment really coincides with each other. So to conclude, we found that this implementation of what we have developed at TNO was able to capture the physics of transitioning flow accounting for roughness, especially at these leading edge roughness heights of 200 microns and 140 microns. Within 10% we were able to capture the experimental measurements. But when we go to leading edge roughnesses in a lower order, 100 microns, we saw that the predictability on the drag forces was slightly deviating. So even though we have a good match on the transition location comparing experiment and CFD, but we still couldn't catch some of the drag increase. So in conclusion, we were happy that we were able to develop something that we can catch roughnesses at the leading edge with a two-dimensional flow environment, and that is representative that we can go on to assess AEP using these results. So now I will talk about the aerodynamic aspects of the scanned blade, which will talk more about how the other order of complexity. Instead of having a general value to define roughness at the leading edge, we've actually used the contours from the scanning that we were able to do at TNO. So to give you a flavor of things, my colleague Harold went into the field with a handheld scanner, and he was able to scan an existing blade with erosion. You can see that he's doing that here on the left-hand side. And we were able to translate that to a CAD geometry. And so on. Here, we use the CAD geometry to make the corresponding mesh around it so we can model the flow within these crevices and pits, etc. So we did two studies here. One is to extract a 2D profile out of these 3D surfaces and conduct a sensitivity study to try and mimic a higher degree of erosion and see what are the impact of that. In parallel, we were simulating the 3D geometry with these crevices. So, before I tell you the results, I want to highlight the effect of lift to drag ratios, which is a crucial parameter that we use to determine aerodynamic efficiency of a section. So that's shown here on the right-hand side. So in the y-axis, we have the lift to drag ratio. On the x-axis, we have the angle of attack. And this, what you see here, is showing the results when we don't account for transition. If we assume a fully turbulent boundary layer and assume some degradation at the leading edge, like it's shown in the top right-hand corner, we hardly see any differences to the lift-to-drag ratio. It really desensitizes the effect of erosion when we have a fully turbulent boundary layer. That was quite an eye-opener, really. But in the natural environment, we find transition flows in general. So we carried on to see what is the impact when you have transition and still have some degradation at the leading edge. And we saw a massive drop of lift-to-drag ratios. It's up to 50% drop in aerodynamic efficiency when you have these kind of degradation at the leading edge. And yes, that clearly shows that the aerofoil is actually 50% less productive in terms of lift-to-drag ratio. So it highlights how much erosion can damage the performance in terms of local performances on the blade. So with this data set, we conducted annualized yield analysis On the top left, I have a table showing the relative differences between SST clean blade and SST LM, which is the transition model environment, between different degree of erosion levels. And you clearly see that the SST column is hardly any reduction in AEP, while the transitioning environment, we see quite a bit of a reduction. And the top table only shows erosion accounting up to 15% of the tip. If we were to replicate this study and assume at least 30% of the blade from the tip was eroded, you can actually degrade the performance up to 1.5%. I have to highlight the fact that these analyses are accounting for higher wind speed as a mean wind speed. If we were to look at this in an onshore environment where the velocities are lower, these AEP reductions can actually go into 3 to 5%. So this, again, we were able to highlight the aspects of erosion in an AEP sense. And on the right-hand side, we see a contour of pressures on the resolved geometry. And what it also shows that under fully turbulent conditions, even though we were able to capture so much details using the scan geometry, we hardly saw any differences on the performances. Okay, to wrap up. So within these two parts, what we have learned is that we see quite significant damage at the tip part of the blade, and we can expect AEP reduction in the order of 1.24% when we have the leading edge degraded by 0.8% of the chord. And then on the second part, we learned that the transition model developed for roughnesses was working really well and producing very good agreement with measurements. And that was able to capture the effect of roughnesses in the order of 100 to 200 microns. And that gives, this simplistic model gives some flexibility for modeling rotor level, where we can enforce boundary conditions now instead of actually meshing the geometrical changes. But we sadly saw that at a lower order of roughness, we failed to capture the drag increase. But yes, it's up for further research. We hope to develop something further to capture also the smaller degree of roughnesses. So in terms of further work at TNO, we are always looking to develop research for roughnesses, and we are currently putting in proposals for doing further work on this. And as one of the further work that also Gerard highlights is the high Reynolds number flows. Currently, with CFD or even experimental data, there's a serious lack of data set at high Reynolds numbers. And we are looking at wind turbines ranging to 15 megawatts and higher nowadays. So I think that is a serious concern for research. And we will work on trying to establish these data set for people to investigate further. And then, of course, these roughness models, I think we will expand that for thicker sections and at higher Reynolds numbers. Finally, I want to indicate that we have a publication with the Wind Energy Science on the same topic that I presented here, but with greater detail, a lot of discussion. It's been peer-reviewed by one of our, actually our guest speaker. I must thank her again, Beatriz. And yeah, please have a read of our publication and share your thoughts on it. Also, I would like to acknowledge thanks to AIRTuB for funding this work, also Ferry for organizing this event, and Sandia for supplying the experimental data. That's it.
Thank you. Thank you, Kishore, for your, well, For me, quite a scientific explanation, but this is, let's
Yes.
say, real scientific research. Are there questions from the audience?
Right. Yes, the scaling in terms of, like Gerard said, the Reynolds numbers will also scale with the scale of the blade. And currently, the analysis is being done on a lower Reynolds numbers. These are not representative to give that. But if we assume that these effects stays the same, then you will expect the same order of magnitude in terms of reduction. But I dare to say that because I know that high Reynolds numbers, that the flow is much easier to go into a bad situation. It will trigger a transition earlier. It will cause more dramatic performance losses. But that's just my gut feeling and experience. We need to find that through experimental work.
And for that, you need follow-up research and new projects. So
Yes.
I see that you are quite passionate on this
Yes.
topic.
Yes.
So it's good to have you in the team. Thanks a
you.
lot for your contribution.
Thank you
and
very much.
I think now we go over to the next presentation. Sorry? That should be Beatriz, and I hope she is online and our people from the technology can organize that she can be seen.
Hello, can you hear me?
Beatrice, we can hear you, but we can't see you yet.
Okay. The challenge will be to share my screen because I cannot do it because it says that only the organizers can do it. So if you can give me access to share my screen.
Of course. I'm going to do that.
Okay.
And I think now you should have access and we can see you. Well,
You can see me very big.
well, it's great to have you in our meeting on let's say aerodynamics of wind turbines. And well, we are very curious to learn what your findings are. So I think the floor is yours.
Okay, thank you very much. So first, thanks to Gerard and Kishore for inviting me to this presentation. Hello to everyone online and everyone there in that amazing building that you have for being there. I'm in Pamplona and I'm at home because we work from home. So I'm going to share my presentation and try to explain in a simplified way which are our research with regard to blade erosion. Okay, I think that in the audience we have like a mix of expertise there, so I will try to do it like not very technical. Okay, so as I said, I'm Beatriz Mendez. I'm a senior researcher at CENER, that is the Spanish National Renewable Energy Center. We are like a small ECN or TNO, like Gerard said, but really, really small. So we are in the wind energy department. We are 20 people working there, but we are very active and we work in many research projects and also for the industry, mainly the Spanish industry in this wind energy. So we have been involved in research in roughness and erosion since 2009 in different fields, especially in field characterization, also in wind tunnel experiments with roughness or erosion or vortex generators. That is something that I'm going to show you afterwards. And for sure, we are really into the modeling using CFD of this erosion and roughness. So first of all, I would like to talk a bit about which are our activities with regard this characterization of real roughness or erosion. So here I have like created a sequence of pictures in order that you understand which are our challenges in this field. So we have a blade. In the first picture, we have a blade. This is a dirty blade. This is not erosion. It's a blade that has been operating in the field, and after several years of operation, the blades look like this, like very, very dirty with bugs, with sand, or I don't know what. So the main challenge that we have found here was to characterize this roughness. Okay. In addition, we also aim to study if the carborundum that
Hello,
we
Beatriz.
use, yes.
We can't see your slides, so I think
No?
you are in the spotlight, but not your slides. Is that something you can change?
I'll try. Sorry.
Yes, yes. Now we can see the slide. Oh, and now you are back again.
Okay, sorry.
Yeah, this is good.
So you see the pictures with the dirty blade?
Yes, that we see. Thank you.
Okay, so I'll start again. Sorry. I'll try not to touch anything. So as I was saying, we have been working in characterization and also in modeling of roughness and erosion. And I created here a sequence of different pictures in order that you understand which are the main challenges that we can face in this field. So first we have a dirty blade after several years of operation. And I mean dirty when I say that this is no erosion here in this picture. So the blades are dirty because of bugs, because of sand. And one of our real winnings was to characterize this roughness and understand how this roughness affects the blades in order to model it both in the wind tunnel and also in using CFD. That means computationally, okay? So in addition, we also were very worried about understanding how this carborundum, that is the second picture that you can see here, this carborundum is used in the wind tunnels in order to simulate roughness. So we would like to understand how this carborundum is and how can be characterized in order to be included also in the modeling. So we use like a technique that is the use of replication resin, that is this green thing that you have here. That is a replication resin, very easy to be used, that you add in the blade surface or in the model to be used in the wind tunnel with the carborundum surface, and it replicates with a very high precision the surface that you have in a real blade and also in a wind tunnel. So once you have this replication resin, you can use a profilometer. That is a machine that produces a 3D map, a very detailed 3D map of the surface that you can analyze in detail in order to understand the roughness. So if we apply this methodology for a carborundum grains, for instance, what we obtain is a picture like the one at the right of the slide. And this picture has many interesting things on it. The main thing is that carborundum is not a regular thing. We have like different shapes, size, and also the density is not at all regular. So with this, what I mean is that both in experiments in the field and both in experiments in the wind tunnel, we don't have regular things, regular roughness, or regular sizes and shapes. And that is the reason why it is so difficult to use it or to model it in a wind tunnel or in a CFD modeling, okay? So one of the main challenges or the things that we should research from now to the future is to really characterize real roughness and be able to model without error the roughness that we have at the field. So another finding that we made in these past projects is that the blades were not as dirty as we expected. Okay, that means that when you model roughness in a wind tunnel, you use this carborundum or the sandpaper, and you expect like big roughness to have a big effect in the power production. But what we found is that blades are dirty in a dynamic way. I mean, they become really dirty after periods of sun or of in summer with there are a lot of bugs. But if you have rain after that period, the blades become clean again. So another challenge here is that the status of the blades, let me say, both in roughness and also with erosions, is a dynamic status. You don't have the blade surface always the same. So it's quite difficult to predict production when your blade is changing continuously its shape due to roughness that appears and disappears because of rain, or also due to erosion that is something that starts to evolve and increase during the year. So there is not a static blade surface, and for sure there is not a static or an easy way to predict that. So when moving to modeling, I would like to focus your attention and not in the modeling as Kishore made, like really technical modeling of roughness, but I would like to focus your attention in the different models and solvers and tools that we have to model erosion. Okay, so these pictures are a comparison of model CFD modeling using WMB, that is a CFD code that we use at CENER, compared with experiments. These experiments are experiments in the HZ wind tunnel that is in Göttingen in Germany. And we have here experiments that compare clean cases that are the black lines with rough cases that are the blue lines and symbols. So what we see in these experiments is that roughness modeling in this code and with these types of models is very well captured. So that is a really nice thing to say, but the point is that this is something like eventual. It is very difficult to reproduce this for different types of airfoil, different types of roughness, and also for higher Reynolds numbers, as Gerard and Kishore mentioned. So in any case, these are like the ideal comparison between simulations and experiments in the wind tunnel. Okay, in these models, we use the two models that are the Gestel and Lane roughness model, and also the knob model. But what happens when we move to a different airfoil compared to different wind tunnel experiments and with very high roughness levels? So in order not to bother you, I only include here a CP curve of this NACA airfoil tested in a Ludolf wind tunnel. These experiments were performed under the scope of the AIRTuB wind project. It was a joint project in which ECN, Ludolf, DTU, and CENER worked. Sorry. So what we did here was experiments in the wind tunnel and also in the field, both in roughness and also in transition. Okay, so if I focus in the roughness experiments, what we have here is that if we model this with OpenFOA, and there is a different code, if we model this for higher values of the roughness, and if we compare with different wind tunnel experiments, what we see here is that we don't have a good match of the experiments compared with the simulation. So these are the curves that are not close to the circles, okay? The green, the blue, and also this orange curve that is on the top. But what we did is to change the model to find a suitable model for OpenFOA and to find like a really good match again between the experiments and the simulation. That is this pink curve that is in the top of the circles, okay? So my conclusion here is again that we have to find models that are like standard for all the types of airfoils, for different Reynolds numbers, and also that are suitable for the different computational tools. And that is something that is not at all easy, and that is, I think, the real challenge in the future. And I will talk a bit about that in the last slide. So, as I said, in this AIRTuB wind project, they also measure the effect over AP the roughness. They included, this is a real blade. This is a picture of the experimental wind turbine that is in ECN facilities. This is an N80 wind turbine, a wind turbine from Nordes, and they add sandpaper in the last 5 meters of the blades in order to test the evolution of the AP. So what they found there is that in the experiments, they found a reduction in AP of about 4%. And what we did, what we obtained experimentally, computationally, using the CFD polar curves that are computed in this left part of the slide, we obtained like also very, very big AP losses due to roughness. These other figures that appear here are the way we design a virtual blade to reproduce this N80 wind turbine that is confidential, so we didn't have access to that. So we use a tool that is called Blade Oasis, that is an in-house tool that we have at CENER to mimic blades. This is the blade geometry, and you can see here the evolution of the genetic algorithm to find the best blade to reproduce the objectives that you are looking for. And the main conclusion after this study is that roughness produces very, very big AP losses in the wind turbines, not only erosion, but also roughness. If I move quickly to our research in the field of erosion, I recently presented in the TORC conference this study in which we did the same scan of blades as Kishore did. Like we obtained the 3D blade of the 3D shape of the blades with the erosion. You can see here the different views. And what we did was to study or to understand statistically which are the effects of these erosion types in the annual energy production of the blade. And again, what we found, we did this computationally using CFD. What we found is that AP loses about 3% maximum and ranging between 1 to 3%, depending on the area of the blade that is affected by erosion, are found. So this is also a big production loss that is not interesting at all, and that we need to fully understand and model in order to find measures or decide when to repair our blades. In this study that I show here, what we learn is that the location in the pressure side of the blade, bigger the effects with corners and closer to the leading edge, lead it to the worst situations in terms of AP production. And finally, I would like to show you some mitigation measures in order not to always talk about the problems, but also talk about that there are solutions. And these solutions are vortex generators that are small devices that are placed in the blades. If you're not very familiar with aerodynamics, but you go to a wind farm, there is very usual to find a blade with these small blades, small vortex generators over the blades. There are small vanes that what produces like a vorticity that maintain the boundary layer attached to the blade surface. So these vortex generators are currently used in blades in the blade tip area in order not to lose as much as power as you can expect when you have roughness or erosion. And what we found, that is something that is going to be published very soon, is that we use vortex generators. We can recover more or less 1.5 of the AP that we lost when we have roughness or erosion. So this is a nice picture in which you can see the way the BGs work. Without BGs, there is separation in the trailing edge of the blades, and when you have BGs, this boundary layer is attached, and so the production goes a bit further. That is the expected thing that we want. These low drag vortex generators that we have at CENER that are not a conventional shape. They are tested in the wind tunnel. But before finish my presentation, I would like some conclusions. That is the thing that I would like to keep in mind is the first of all, we need to standardize roughness models for CFD simulation, and also a definition of the erosion categories to make a catalog in order to standardize all the process to understand the power losses due to roughness or erosion. Both of these tasks are being performed in the IEA task 46 that is devoted to blade erosion. It's very interesting. If you are not familiar with that, you can Google it and understand which is the work that is performed there. And also my conclusion is that we need to make or to have decision maker tools independent from CFD or for very complex computations in order to be used by the industry and to decide where to repair our blades, which is the best moment to repair our blades. And finally, we need to advance in new mitigation measures for mitigate the effect of erosion and roughness that they are for sure there in the blades, and we need to fight against them. And that's all. Thanks you very much. These are some publications in this field. Thanks for your attention, and if you have any question, I will be happy to answer them.
Well, thanks a lot.
Thank you.
Well, then you already asked for the questions. Are there questions? I think Gerard has a question. Can you hear us, Beatriz?
Yes, very well. I cannot hear her, and maybe you can translate him. Okay.
Here's a microphone.
Perfect. And now?
Yes, perfectly.
Okay. Well, first of all, thanks a lot for your interesting presentation and the great work you are doing there in Spain. Yeah, and we also have to talk about this Nordic 80 issue because we do have these turbines were owned by us. But I wanted to ask you, can you elaborate a little bit about the difference between roughness and erosion, because it's always used in one term, and for me, roughness is more an addition to a blade. You mentioned sand or insects, for which rain is good, actually, because it takes away the roughness, where erosion is more something which is taken off from the blade, and mainly because of rain, I think. So there, rain is something negative. But I always have the idea that from an aerodynamic modeling point of view, the difference is not so essential, but maybe I would like to hear your opinion on that, actually.
In my opinion, they are quite different because in the roughness level, you have small things that affect the boundary layer in a soft way, but with a big effect. Let me say it like that. But in erosion, you have big spots with a big loss of material, and the flow can go inside that bigger spots. So the effect over the flow is completely different. So they affect for sure both of the types, roughness and erosion, affect the boundary layer, producing change with regard to clean conditions. But the affection is completely different. But I'm not sure if we are ready today to find or to specify the differences of that, because we are all the time looking at the AP losses, but maybe we need to go a bit earlier in the process and understand how the flow is there, and in order to find nice mitigation measures for that.
Very clear, something to think about, yeah.
Okay. Well, thank you for that explanation. Are there more questions in the audience? I think Kishore has a question. Maybe, Gerard, you can hand off the microphone.
The aerodynamic guys has questions.
Thank you, Beatriz. Really nice presentation. I'm also quite excited to see the mitigation methods with VGs, as my PhD revolves around VGs. And currently doing erosion as a mitigation technique. It's fascinating. I just wanted to ask, have you looked into the the actual benefits in terms of the drag reduction with the VGs and without the VGs at the tip part?
Yes, I didn't elaborate it much because I saw that I was taking much time than expected. But yes, these low drag vortex generators that we designed at CENER in 2020 in also an European project called ODB. These airfoils are these VGs are designed not to add as much as drag as the conventional vortex generators add to the blade surface, okay? So these vortex generators are designed based in aerodynamic shapes. Yeah. The cross-section of these vortex generators is a low drag airfoil, symmetric airfoil with a very low drag, and very thin also is a 10% airfoil. And designed specifically to add low drag, and we have publications in which we compare these VGs to the conventional one, and they add drag, but not as much as the conventional VGs. Okay, but this is something also tricky because you have to find the right location of these VGs because they have to be perfectly placed in order to produce a positive effect in the boundary layer. And also their height should be also the right height in order not to produce a bigger or a lower drag. So you have to study these vortex generator effects like for every different case, and that is something very complicated because it's very manual. So the idea is that we in the future have like mitigation ways that are not so dependent of the flow characteristics. Okay.
Right. Yeah. Thank you. Yeah, it's also complementary to the industry nowadays. I also see pictures of blades with vortex generators up to the tip. So I think we are in the right path for mitigation technique. Thanks, Beatriz.
Thank you, Kishore. Yeah. Nice to see you. Yeah, nice to
see you too. It's good to hear that we are on the right track, and thanks for your contribution to our meeting with your insights. Very valuable, I think. And for the audience, now we have a pause. So Beatriz, thanks again. And
Thank you, bye.
well, you can stay with us, but we will have a pause, and afterwards we will continue the program. And I'd like to say that well, if we stick to the original planning, we have a pause of 15 minutes. Is that enough? I think we can do with it. So we'll be back at around 3 o'clock. And I hope the online audience is back then as well. Thanks for now. I think I should say lady and gentlemen. We are so pleased that there's one lady in our middle. At least in the audience. And then I mean in the live audience, because to be honest, I don't know how many people there are in the online audience. I've asked to get some figures there, but I didn't receive them yet. But I hope we do have, well, at least as big as our live audience we have online. Let's see. We are now starting for the second part of our, well, let's say, program. And this is mainly about the word packages 4 and 7. And we have, I think, 3 presentations there. And I think Loek is already popeling to start. I don't know if that's, that's a good... Loek, the floor is yours.
Good afternoon, you all. Since I'm so popeling, I will start then. Let me first start by saying that I'm definitely not a specialist in aerodynamics. I'm a software engineer by education, and I've turned data scientist along the way. So this was actually a very interesting project for me to do, because I had no clue whatsoever about wind turbines. I know that they spin and they generate energy, and that was about the extent of it. So. I teach at the HZ University of Applied Sciences. I also do research there for our research group Data Science, together with 8 other researchers. I think it's good to first ask ourselves why we should even think about using machine learning to classify leading-edge erosion in wind turbines. To keep in the Dutch proverbs, Ferry mowed the grass in front of my feet a bit, but let's still do this. From a maintenance perspective, wind turbines are in the worst location possible. They're far out at sea. They stand next to highways where you can't easily get to. They're often next to canals or other bodies of water. The blades are very high up. They're unwieldy. I have extreme fear of heights, so even looking at a wind turbine and then thinking that you would voluntarily go there and inspect it is honestly frightening to me. But fortunately, photography drones have made things a lot easier. But even then, it's still hard to do leading-edge erosion detection because you still need to interpret the photographs. I've been told that the new wind turbines at sea have blades of at least 80 meters, and they're getting up to 107 meters. And if you need to inspect a blade millimeter by millimeter, that will take a very long time. And on top of that, there are only so many people who can do it. I've found this table at CBS, which tells me that last year there were 2,400 wind turbines on land, and if you include the ones at sea, which I got from this very nice infographic that the government gave me, we get to a total number of 3,500 wind turbines. And a very simple calculation in my head says that if about 10% of your wind turbines need to be inspected every single year, then it's pretty much a 24/7 job for a team of people. So it's quite hard. And apparently there's some energy crisis going on, so there will probably be a lot more wind turbines. So wouldn't it be nice then, I love music, so if you see some music references, then that's why. Wouldn't it be nice then to have a drone that can fly to a turbine, scan its blades, automatically identify what parts of the blade have eroded, and then apply repairs on that blade? And the bold part, the automatically detect and classify erosion, is where I came in. There was one small problem though. What are the classes of erosion? Because there is erosion and there's a lot of erosion, but how much is a lot and how much is not a lot? So I searched on the internet for pictures like this, which still didn't really tell me anything because the 1 year in service looks worse than the 2 year in service. But fortunately, there is quite some literature out there, and I had quite some help from external people as well to gather domain knowledge. And in the end, we got to this table on the left. I blatantly stole the images from a paper you see on the right to give an indication of what the erosion classes are that we're talking about. So we are ranging from very small pits that are less than 0.2 millimeters in depth with a very small area of less than 2 millimeters squared. And we get all the way up to delamination, where which you just saw in the pictures before, where the leading edge is completely eroded off. So class 5 is the worst you can get. Class 1 is the best erosion you can get. I also found a very nice picture online that basically resembled what I did, so this was a very nice picture. On the right you can see no erosion, and then to the left you can see 1, 2, 3, 4, 5. So that was work package. That was the first part for me. Now I had my classes of erosion. I could actually start. In other words, I could data science the heck out of this. And very helpful to me was work package 1. They had a laser sensor and they scanned a blade for me. All the details are in the paper here I linked, but I snapped a few screenshots of it. For example, this one. On the left are some very eroded blades with a lot of damage, but on the right is the more interesting bit. Is where you can see that there is a laser sensor attached to a drone. The drone is flying over a blade, and all the while it's flying, it's scanning the blade, which is the red line you can see. This was also tested in the lab, so it was not on the drone, but it was tested in the lab. And on the right you can see the very impressive laser sensor. It's about 1 meter big, so it's quite an impressive sensor actually, with a dummy blade on the left that they scanned. And work package 1, for example, was able to make pictures like these, where you can see in different methods, different ways of displaying the erosion that is on that blade that is scanned. Personally, for me, this blade was actually useless because it was all class 5 erosion. Didn't matter where I looked, it was all class 5 erosion, so training machine learning models on this thing doesn't do much because it will always predict class 5, which was correct. Fortunately, I think it was NLR actually scanned the blade with a laser sensor, and on that blade they had glued a very thin layer of paper of 0.2 millimeters deep, which was quite nice since that corresponds with class 1 and class 2 of my erosion table. And they made different patterns in it, so hopefully you understand my very bad drawing of what I tried to display. And if you take that scan and you prepare it a bit and make it look nice, it starts looking something like this. So you can see different erosion patterns, like very big ones like here, or some smaller ones here. And on the very right here, we actually discussed what it was we're seeing, and we came to the conclusion that it was probably dots of glue that was used to apply the paper. So in the end, we concluded that this was not erosion. If we zoom in a lot more, you can actually see the different lines that the laser scanner made. So this is also pretty cool to look at. It's zoomed in so much you can't really see the erosion anymore, but if you look through the hairs of your eyes, you can probably still see it. So then it was time to actually do the things we wanted to do. This is a comparison of what Word Package 1 did versus what we did. I won't bore you with all the details. We're just going to focus on this one. So what I did was I created slices of 10 laser lines, which corresponds with about 10 millimeters of blade. Sometimes it's 9, sometimes it's 11, but on average it's 10 millimeters. And on those slices of laser lines, I trained 3 machine learning models. The first 2 models are linear models, because there's a very linear correlation going on with erosion. The bigger, the deeper the erosion and the wider the erosion, the higher the category, which is very linear. But I also trained a random forest model, since those surprisingly are quite good on pretty much any data set you throw at it. So just to see what would happen. There is a disclaimer though. In the end, I ended up with a scan of 1 meter of blade, which corresponds to 98 slices. I had to throw away 2 slices since they consisted of entirely of null values, so there wasn't anything in those slices, which means that my results are very limited, and I also don't have data available on category 3, 4, or 5 erosion, so the worst ones. On the other hand, you could construe this as a positive, because if we're able to detect really small patches of erosion with machine learning, then we'll probably also get the big ones. So the goal shifted here to showing that our proposed approach actually works, instead of creating a full-blown tool that will automatically classify and detect and generate repair recipes. As a good data scientist does, I split up my data set. So there's a train data set, which I use to train my models, and there's a test data set, which my model has never seen before, that I use to evaluate the model. This was actually quite hard to do, since there are only 9 slices of category 1 erosion, so we need to have a representative sample, but we figured it out. I'll give you a very short crash course on machine learning, because machine learning always sounds nice and nobody has a clue what I'm talking about every single time, so I'll give you a very short crash course, since I'm a lecturer after all. On the top here, you can see traditional programming, what I was taught to do as a software engineer. You have some data, the engineer writes a program, then the computer does stuff, and output comes out. In machine learning, you do some very weird stuff. Namely, you give a computer some data and the outputs that belong to that data, and let the computer figure out the program. And if you have that program, then you give that program to a software engineer so he can do the top thing, and then actually create a cool tool out of it that you can use. As I said, I have used 3 machine learning models, which I will give you a very high and hopefully somewhat humoristic overview of. All the examples I use are 2-dimensional, even though my data has a lot more dimensions, but just so you sort of understand what I'm talking about. If you have a point cloud, you can usually draw a line through it. This is what we call linear regression. This hopefully won't be a surprise to anyone. If I really abuse this line and use it to divide my data into two classes, I get a logistic regression. So it's a regression model that I use to classify. And this is the first model I use. Now let's play a pub quiz, because you've been listening for way too long already, and you need to do something. I'm going to draw 4 lines, and I'm going to let you vote on which is the best line. So first I have this yellow line. I have this orange one. I have this green one. I really hope there is no one out here with red-green color blindness. You have actually, oh, that's interesting. The last one is the green one. And I'll have this weird blue one. Who votes for A, yellow? For B, orange. For C, green. Thank you very much. Very intuitively, green is the best line. Why is that? Because the distance to the data is about the same on both sides. This is a very useful thing for a machine learning model to have. So if new data comes in, you have the biggest chance that it actually ends up in the correct category. And my support vector machine can abuse this. Now draw a line through this data set. Doesn't really matter how you put it, you are going to misclassify about 50% of your data. But I can pull a very cool trick. I can add another dimension to my data, then draw a line through it, transform my data back, and now I've proved that the circle is a line. And if you're thinking data scientists are truly madmen, you're getting there. But this is something that my support vector machine can also do, which makes it really cool because it can transform data into other dimensions and then use it to draw cooler lines to it, through it. So support vector machine is actually a quite advanced machine learning model, and I hoped it would do really well. The last model, you've all seen a decision tree. Hopefully this shouldn't be too difficult. But if I take, let's say, 100 decision trees, like I did for my random forest, I can train all those decision trees individually, let them start at different points in my data, train them individually, and then I let them vote very democratically. And in this case, 3 out of 4 decision trees vote 1, so that means that my random forest will say 1. This is a very intuitive machine learning model, and it's amazingly very good at pretty much any data set you throw at it. If you're thinking, dude, machine learning is just glorified curve fitting, you're completely right, but my model is bigger than yours. My model can use 75,000 data points, and yours probably stops at 6 or 7 parameters. Mine can have 75,000. And that's nothing compared to deep learning, if you want to go there. But let's see. So we have this zoomed in slice, which I zoomed in scan, which I took slices of. So here, for example, you have 1 slice. This slice consists of about 75,000 data points. So there's 10 lines in there, so about 75,000 data points. What I did was I took 75 of those training slices sort of randomly, because it still needed to be representative. Then my computer did all kinds of stuff I cannot possibly understand, and out came a model. Then I used that model, along with my 33 other test slices, to get some results. So for example, in this case, slice 1 would apparently has an erosion category of 1, and the location on the blade is there as well, because that's kind of useful to have. Very short sidestep. Usually when people ask me stuff as a data scientist, they think this is all I do. That's definitely not the case. Creating these test slices, for example, takes about 80% of all the time I put into your project. So for example, in the case of AIRTuB, to get to these slices and actually create them as you see them there took me about a year of meetings, coming up with processes to process the data and then validating all the results with domain experts, because I am not a wind turbine specialist. I don't know what I'm doing. My computer is not your run-of-the-mill computer. It's really quite good. And just making that picture there costs my computer about an hour to do, because it's really difficult. Training the model is actually only 20 seconds of time. I can train multiple models within a minute. Actually, predicting with my model takes about a millisecond, so that's not that hard. Data science, about 80% of all the time you put into data science is making sure that your data can actually get into the model. So if you have a data science project of a year, start expecting results in like October or November. There is a very interesting paper made by Google if you want to know more about this. But now, all you're here for, show me the money. But first, I want to show you two benchmarks. I've assumed two very bad models. The first one is that my model says that there is no erosion. No matter what I put into it, it's always no erosion. And I also have a benchmark where my model predicts everything as the worst category of erosion that's in my data set. The reason I do this is because if my actual machine learning model predicts worse than these ones, then my machine learning model is worthless. It hasn't learned anything. And we want at least better than coin flip. So if I would flip a three-sided coin in this case, no erosion, class 1 erosion or class 2 erosion, I want my model to do better than this. I won't bore you with the exact interpretation of the metrics. You're seeing three numbers. If they go up, that's good. If you want to know what they are, please find me at the drinks. This is the worst model, probably, which is my benchmark for everything is not eroded. As you can see, interestingly, it actually does better than coin flip. So this is already interesting to see. In my data set, just predicting everything is not eroded is already a reasonably good model. If you predict everything as class 2 eroded, that's actually an even better model. So that's also really interesting, because all the numbers went up. Now if I throw my logistic regression at it, you can see that the numbers get really better. So fortunately, my machine learning model is learning stuff. And if we get to the support vector machine, we actually get to the best model out of all of them. And about 2/3, as you can see, of our data set is going to be classified correctly. You can also see in the table on the right that it has a real difficulty with class 1 erosion. Which is probably because there are only 5 data points it can train on, which is about the same if you would ask a 3-year-old to recite the entirety of King Lear. It would probably get a few sentences right, but not most of it, and that's really what's happening here. I have too little data. Then the random forest also does quite well, but it does worse than my logistic regression support vector machine, which makes my support vector machine the best model out there. I was actually quite impressed by these results, because usually when I have so little data, I get a lot worse results, so I was quite happy with this. Also, if I have more data, I can pretty much guarantee you I would get better results. So if there's ever an AIRTuB 2, please give me more data. If you have technical questions about how I did all this, then find me at the drinks. I'll share code, that's fine. Some conclusions about the process. We were able to identify 5 classes of erosion. We were able to prove that our workflow that we proposed actually leads to results that you can use, which Ludolf will talk more in just a bit. We were also able to prove that machine learning can detect small patches of erosion, which is good to know. On the other hand, if you would do online processing on the drone, it would probably fall out of the sky, because you would need 4 hours and the battery just doesn't last. So for now, it's either offline processing or sending all the stuff to a data center, let the data center process it and send it back to the drone. If you have any questions, find me afterwards, I guess, or maybe we can do one question now. If you want to do a project with us, email address is right there.
Thanks a lot, Luke. And now I understand why you were popping, because this is interesting stuff, and you explained it, at least in my opinion, in a very clear way. So thanks for that. And the results are apparently satisfying.
I can do better, but they're satisfying. Yeah.
They're satisfying. Yeah. That's good to hear. Are there questions from the audience? Not for Kishore has one question. Yeah. Oh, you can share the microphone. There's another one.
Thanks, Luke. Really fun way of presenting. I really enjoyed it. My question is on your last comment about 4 hours. But isn't that contrary to what you said about after you develop the model, it takes a really short time to get the output? I wasn't clear on that.
Fair enough, I hadn't explained that, so to not bore you with all the details. I need to pre-process all those individual laser lines first, and that takes 4 hours per meter. So that's why the drone would probably fall out of the sky. Yeah, because I have tens of millions of data points, and I can remove about half of them because they add no value, and the other half I need to process well to actually get to the usable input data. Yeah.
Can you put machine learning to do that on top of this?
Can I put machine learning to do that on top of it? If I have enough data, yes. But then you would need probably like 20 or 30 turbine blades to get to that point, yeah.
Okay, I think we'll leave it here for the moment because we have 2 other presentations to go. So thanks a lot. And by the way, you showed us nice pictures of, let's say, the setups at TU Delft as well. And there we saw this big laser line scanner of 1 meter. But I know that it has already been flying under the drone that we developed in the project. So are they, let's say, decreased it in size, or the drone can carry it? I don't know yet, but we will see in our final, let's say, end meeting of AIRTuB at NLR. So, but thanks a lot for now. And then we go to, let's say, the next presenter. And I think the next presenter will make use of the data that is generated or interpreted by Luke's findings, and that is Ludolf Pijpker, and he is in charge of work package 4 and 7. And well, I think, Ludolf, you can introduce yourself, and the floor is yours.
Yes. My name is Ludolf Pijpker. I'm working at Stork AMT. And yes, I'm a work package leader of 2 work packages, 4 and 7. And I'm not a data science, so for this work packages is the thing to translate every nice data science result into a kind of business case. What are the benefits of what we have learned in this project, and how can we translate it to actually money? What is the difference between the baseline that Eneco has doing right now? So that's the big challenge. So first, a little short about work package 4, because Luke already told some parts of it. But it's about the acquisition of data. So what kind of data we have. Existing data from their SCADA DCS system, they call it Breeze. And so that's about historical performance data, but also, of course, the new sensor data that's already shown from the laser scanner and also from the crawler. And it's about cleaning, enrichment, see what we can use of the historical data, and yeah, that's about work package 4. A little bit about existing data, historical data. Luke investigated 3 years of data from 3 wind turbines, 30, 56 and 58. And there were different kind of wind turbines. One of them has different coatings, and one of these 3 had also a leading edge of a kind of protection, polytest shells. These are protections on the leading edge. And so it was good to see if we can use that data to see if we can see a difference after some degradation in the annual energy production that they see. So, and also look at the influence on the position of the wind turbine, and that's etc. Quickly to the conclusion that Luke made. That's very difficult to use the existing data. A lot of cleaning has to be done, And at the end, even with 3 years of data, there were limited data lines that could be used. And based on that, so there was not a clear view of degradation of losing that amount of energy production, of performance for those 3. So I'm not talking about, I'm talking about the historical data from the existing data that's available. We see for theoretically, yes, we have seen, and Gerard and Kishore have also shown that there's a potential for having, that there will be losses after some degradations, depending on the categories of failures. This already Luke shown, so we looked also to new data. Luke has shown that there will be an automatic categorization of defects, very good to have. And also the position where these defects are. So the categorization of the different classes are possible. And for the crawler, there for critical points, there are information is about the position and the size of the structural damages are shown. But you need a diagnostic engineer for it to translate it to the right, the size and the position of these kinds of failures. So this is about the new data. So it's usable. In particular, the laser scanner on the drone, as Luke also has shown, is very usable for our new scenario, new business case compared to the baseline. I switched to the business case for work package 7. So we looked at the baseline, the existing maintenance that Eneco is doing right now on these wind turbines. They have 60 anomalia field. And as in the next slide will be shown, there are a lot of different strategies they tried and to experiment on to have an indication of the state of the blades. And for this in the business case is to compare the baseline to the new scenarios with a drone, with a laser scanner, and also some futuristic scenarios with what I will show in a minute. Yes, and how can we dashboard this kind of data, the state of the blades? What's possible? How to indicate? Okay, you have to go to the wind turbines because there's an indication of failures based on the trending and modeling what we have done. So how can we dashboard it? It's also part of this work package. So it's kind of a challenge because, like I said, they changed the strategy since 2018, going from rope access to using a camera on a drone and experimenting on these kind of activities. And this picture I received from Eneco that gives an indication of what they changed over the years. So at the top left, you see that they also try to use the telescope camera from a distance to see, to take pictures and to indicate what kind of defects are there. The drone with the camera we used as a reference, as a baseline in our scenario. And of course the traditional rope access that they do. And also an internal robot camera inside the blade and checking making pictures and making tests of the inside of the blade. And for the repairs, there are also different solutions they use and try to see if this gives them extra information or, And there are different possibilities for repairs. You can also take a blade off. If there are severe damages, you can take a blade off and use a big ship to repair it on the spot and then exchange it to the next one. That's also a strategy. I indicate this because they learned a lot, Eneco. They tried a lot and they learned a lot what's in their quest for the maintenance strategy. They learned a lot, and this AIRTuB, what we are doing right now, helps also a lot to see what's possible for a different kind of strategy for their maintenance of the blade, so the inspection and the repair. For instance, they also experiment with different kind of coatings, Lab 9 or BSF. So there are a lot of different kind of techniques they tried. this already I skipped. So in the yellow left, you can see the different kind of baseline we took into account. So the baseline one is the traditional one, the rope access, and they still do a lot of rope access to inspect and to repair. And the second one, baseline 2, is using a camera, 4K camera, to inspect. They look at the pictures and see what kind of category they see on damages leading as erosion, and they plan a campaign for repairing. So we looked at, okay, what are the new scenarios to look at? What you have learned from AIRTuB, and what are the futuristic scenarios? So scenario 1A is about a large drone, our drone from AIRTuB, the big drone with the laser scanner on it, and also the crawler for the structural damage, the inspection of the structural damage with the sensor on that. And the benefits, as you look at the beneficial comparison now with the baseline, that for scenario 1A, yeah, we can actually see that there's a better classification possible, as Loek has shown. There's less repair time because you know in a better way, more accurate, what kind of classification you can expect if you repair it with a campaign. You don't have that much surprises. So there's a learning curve. You can do it more often, but you can learn what you have seen with the laser scanner, far more accurate. But the downside is that you, the repairs has still to be done with rope access, and the logistic cost will be lower, but in the long term, because you need a bigger drone, and for a bigger drone you need a bigger ship to transport. So that's a little bit a disadvantage of that scenario. Now 1B is more that you do also the repairs with the crawler. And 2 is more that more for the future, if you have a hub on the location over there in the North Sea, and you can start to inspect more autonomously from the hub and do the inspection and the repair from there, you save a lot of money for logistic costs. And it's not investigated on, it's not part of AIRTuB 1, but we took a look at it for, okay, what does it mean if you have this kind of scenario, if you have a hub? So yeah, you can do very quickly the repairs, and you can. But the investment for the hub and the investment also for a more complex controller for the drone, and you also have to do more investment for the crawler itself. Scenario 3 is more if we use the laser scanner on a smaller drone for the inspection, and we use the big drone for the crawler to do the structural inspection on critical points with the big drone. So you make a comparison of a difference between the inspection with a smaller drone and the repairs and the inspection for the structural damages with the big drone. You still have the better classification compared to the baseline. And there's also a big learning curve because you know a lot of how you can monitor, you can make a trend, and you have less logistic cost because you use a smaller drone for the laser scanner. But still, you have some additional cost for the crawler because you do an automatic repair with the crawler. Which scenarios that we have discovered? Okay, this will be the best scenarios. That's 1A and 3. So we took a better look in these, particularly the scenario 1A. And Vinit will, after me, will also look specifically in scenario 1A for more detail on the tool he has used for specification, the logistic cost, etc. So 1A and 3. To give you an idea what we have dealt with in what's important to when you make a business goal, a case, we have a lot of variables to take into account. It's about labor cost, how many vessels you need, what kind of vessel, because the different costs of the vessels. Do you need a drone operator? How many drone operators do you need? In Amadeveld, you need an operator to pitch the blades, to put it in the right position. It's not manually done. If it's not automatically done, it's manually done. You need an operator for that. And how many bad weather days do you expect? And Vinit will also elaborate on that question. So for the repairs also, the category 1, 2, and 3, by the way, 80, 85, 90% of the defects are category 1, 2, and 3. 4 and 5 are only 5, 6, 7% based on historical information from Eneco. So that these kind of failures can be planned in a campaign, and category 4 and 5 are more severe, and then you have to act very quickly and very quickly to fix these kind of problems. So a lot of variables to take into account, and that's why I will skip this one a little bit. We looked at these scenarios and we compared it, and this is an estimate, a preliminary estimate on if you compare the new scenarios with baseline 1 and the new scenarios 1 and 3 with baseline 2. Baseline 2 is the 4K drone, 4K camera with a small drone, and baseline 1 was the rope access. We can expect, if we calculate these and use these variables with the best estimate and using also historical information, historical data, that savings on maintenance costs can go to 30 to 60%. And for baseline 1, that's the rope access, the traditional way of inspecting a repair. And also baseline 2 has a significant cost reduction. And why is that? Because you can save quite some money on the duration of the inspection, and also the frequency of inspection, because you know far more what you can expect with a laser scanner, and also a big learning curve because you have a number of time done your inspection, and you can use also artificial intelligence for it to have a better prediction. And of course, the logistic costs are far less than if you use a small drone for scenario 3, and then you can save quite some money on the maintenance side. If you look a little bit more in the future, for talking about the hub, then you can, of course, the logistic costs are reduced to the minimum, and you can save a lot of maintenance costs, inspection and repair costs for that part. Where can it go through? Like if you talk about dashboarding, when you know what kind of you use the laser scanner, you have an automatically categorization of the defects. You can, based on some, you can show the position of the defects, which category is on which part of the blade, and also you can indicate a kind of health indication based on a smart rule. So if the number of failures is larger than this and the position is over there, then you can have a kind of sophisticated rule of a health indication, yellow, red, or green, etc. So this is, at the end, very valuable information about, for Eneco to have in one overview to see what the health is of a blade, and also which kind of categories you are shown on the blade, and then you can plan your campaign more accurate, and you know what you can expect. The last slide. Of course, the development, the technology development is going very rapidly, and we see that if you use smaller drones, the blades constructually are far more improved. I showed you the protective shells on the leading edge, that are used, and are. Eneco has placed, I think, 80 or 90% of the blades of the Amalia field has these protective shells. And nowadays, from the factory, the blades are more equipped with these kind of shells from the factory itself. And the technology is improved. If you talk about hub stations and smaller drones and autonomous inspection, and you see what kind of learning curve you can also use having these kind of techniques, then the logistic costs are going far less than and going less and less in the years. So there's a big correlation in looking at the future on the technology development and the learning curve compared to the logistic costs. So this was my part of the presentation. So if there are any questions, please ask.
Well, let's first give Ludolf a hand. And thanks for your let's say for your part of the project, the presentation. And indeed, are there questions? And apparently not. I do have a question, of course, okay. Because did you also take into consideration the reduction in downtime, which let's say results in the end in the annual energy production? It has its impact. Is it part of the model as well?
Yes, we calculated the downtime that's due to the inspections over the year, and then what time is needed to inspect and to repair. Okay. And then compared also in different kind of scenarios. Yeah, we did. Yeah.
Okay.
And that.
It's good to know. Those are significant figures that can be, let's say, that the result can be. So it's interesting to further develop this research, I think, and see if we can work towards this fully automated inspection and repair facility, I think. Okay, thanks a lot for now.
Yeah, you're welcome.
And I think now we have our last presenter, and that is an online presenter again. And that is Vinit. We already mentioned his name before. I think you have to turn it, and then it will fit in. Yeah, like that. But I don't know if he is online already. Well, and I see that people from the technique nodding. So I think I have to admit him. And now I see our last presenter on my screen, and now everyone can see him. Vinit, can you hear me?
Yes, I could hear you.
Well, that's great, and we can hear you as well. And we just finished Ludolf's presentation, well, now it's your turn for your contribution and your further explanation on the findings in your part of the AIRTuB project. So I'd like to give the floor to you.
Right. Thank you so much. Just a quick one. I need an access to share my screen.
Yeah, I realize. I think now you are able to share your screen.
Is that visible? If someone can just give me a thumbs up. Yes.
And we can hear you.
Perfect. Right. Yes. So hello, everyone. Glad to be here, part of this AIRTuB event. My name is Vinit, and I'm part of TNO. We have a well-represented team already in the event. Unfortunately, I was not able to make it, but glad I'm able to make it at least virtually. The work that I'm presenting today is the work following Ludolf's presentation, AIRTuB's business cases, which were defined. But now the modeling is shown using the TNO's in-house built O&M planner tool. So just a brief explanation what this planner tool was built like. So we have this TNO logistic-based simulation tool in which the inputs are defined, basically typically using an Excel sheet. And these inputs are from the O&M operators, wind farm operators. And this is typically done using their inputs, which is based on the schematic what I've shown here. So we have details of wind farm layout, cabling, vessels, routes, technicians, spare parts, scheduling, weather data as well, and harbor cost. And just for the sake of completeness, like I've also indicated a figure on the right, which is currently the way the TNO Planner UI looks like. So a user could nicely interpret while modeling these Excel-based inputs into a graphical user interface. Some advantage of using this TNO O&M planner over other Excel-based calculations, which are typically the conventional way at this moment, is you can model some very fine-tuned details like transit time between turbines. So let's say we typically have these longitude and latitude data of the wind turbines, where exactly these turbines are located. And from the port, you can model these exact transit time, taking into consideration the vessel speed and so on. Another interesting advantage is we use a metocean hindcast weather data. So we have 20 years of hindcast weather data that is stored inside, which we use to model the weather uncertainty. And this will be a little bit more clear as I take you through some next slides. So before diving into the actual numbers, it would be nice to indicate what key performance indicators that we would be talking with respect to these numbers. So during the course of this research, we investigated different KPIs, the one that is listed here. The first one being the project duration. So we indicate the project duration in calendar days. Next being the project cost, which is the sum of technician cost, vessel cost, harbor cost, and that gives us the total cost of the O&M operation. And lastly, we that was also mentioned during one of the comments, like we also take into account wind farm availability, which typically is the period in percentage that wind turbines in a wind farm are available for operation. So following Ludolf's presentation, I wouldn't really deep dive into the scenario, but just to give you a recap, first scenario that we touched upon, called the baseline scenario, is for the rope axis, where we have 60 wind turbines of the Princess Amalia wind farm with four CTVs deployed and 12 technicians doing the work in this case. So typically, what you see in this table, I have made it a consolidated table in which you see three different columns. First one being the calculation, second one being the TNO O&M planner. PW indicates here the perfect weather, and TNO O&M planner results for 3 years, which is the average of 3 years using some weather data as well in this. So one thing to highlight would be the duration days. So if we compare the duration of the rope axis scenario, the calculation or a typical Excel-based sheet would give us 15 days, which is rightly matched using our tool when we model a perfect weather. But what is different in this, while modeling this logistic-based scenario, is when we take into account some weather uncertainty. So not every day is a perfect weather where operations and maintenance could be performed. And this led to a delay of 4 days in this case, which is indicated by in the duration KPI. I would touch upon the different KPIs as I progress with different scenarios as well. So the second scenario that we started looking at is also a baseline scenario, but now using a 4K camera drone. So again, a quick recap, we have 60 wind turbines. Now the O&M, the inspection is performed using 2 CTVs, 4 technicians are used. And as you see from the figure, we have a 4K camera drone doing the inspection on the blade. What is also indicated in our simulation is a yield-based availability. Definitely, we do not have the availability made available for the perfect weather, but we do have for the 3 years, where we average it out, we see a yield-based availability of 99.94%, which is quite higher as compared to the rope axis, which shows that the availability with respect to the rope axis is at an advantage when done by drone inspections. The last scenario that we touched upon is a AIRTuB drone case, where again a quick recap: 60 wind turbines, and this time we have one CTV and one SOV. The SOV for the reason because from the user inputs we were shown that the AIRTuB drone is large in size, which demands a larger CTV. So that is the reason for the modeling purpose we considered an SOV for this case. Again, 4 technicians were used for this scenario modeling. Definitely, as I mentioned, a larger vessel in this case resulted in a larger cost as compared to the previous scenario. So a distributed split up of different KPIs are indicated here. So what was also interesting while modeling these scenarios, we also developed these custom weather limits within the tool, which allows one to set different parameters. So let's say like in the table, in the figure that you see on the top left is what you see a custom weather limit set for the wind speed at 100 meter, which was 10 meters per second. So this could be more or less, this was one of the user input that we defined based on the operation for the drones, which is considered as a safe operation limit for the drones. And this was iteratively repeated for different scenarios as well. When considered for rope axis, a different custom weather limit was used, and so on. The O&M Planner tool also allows us to have these work order distributions split into Gantt chart. So what you see on your top right figure is the distribution of the Gantt charts in which the work is shown in a distributive pattern. So the green one is where the work is actually happening. The yellow block within the major block indicates where the transit is happening. And if you just notice, there is a block with a light green with a dark black cloud, which indicates a weather delay. So weather delay is something which is modeled using these metocean hindcast data. So when we model this historical data, you could take into account these weather delays, which are rightly modeled in the logistic scenarios. And the last figure that I indicate on at the bottom is the monthly accessibility comparison. So just imagine if I want to do a parallel comparison of conducting an inspection in the month of May and the same inspection in the month of November, that is in winter. So comparison of a summer period and a winter period. The weather uncertainty that is taken into account in the modeling tool gives you a reasonable approximation that, for example, what you see in the top part on the May 2nd, that being Wednesday, and May 4th, I have a weather delay. But if you compare that to the month of November, I have a weather delay of 5 days in this case. So a summer period and a winter period could be compared in parallel. So this is one of the features that we also used while making a comparison of the monthly accessibility. So in Ludolf's presentation, there was this term, learning curve, that was repeatedly mentioned. So let's define this learning curve a little bit further. So a learning curve typically is a trend that measures the progress of a specific metric. In this case, the metric could be the duration, which is the y-axis in days. And as the number of inspections go higher, the duration or the metric goes lower. So we learn from the data, and based on that training data set, your metric goes lower. So this is what we use to just define another scenario. So what you see as a goal is a visual inspection and a repair using an AIRTuB drone with a laser scanner now. So typically, for the scenario, we consider 12 wind turbines of the 60 wind turbines of the Princess Amalia wind farm. And in this case, we deployed 4 teams with 3 technicians each. So the idea is the 4 teams would repeat the same task over loop. So they would repeat this task 3 times to complete this inspection scenario. So what you see in the highlighted portion is the core duration of the work, which begins with 6 hours for the loop 1. What you see at the top 3 blocks. And as we progress gradually, the duration reduces from 5.7 to 5.42 in this case. Another interesting block that is the uniqueness of modeling using the O&M planner tool was also the total duration, in which we had some delays that are encountered. So we notice a delay of 24 delay indicating a 24 hours window there, and also 11 hours. And this is accounted for the weather delay, which is indicated by this Gantt chart at the bottom. So to conclude the work, I would say the simulation results indicated that inspections and repair carrying drones is more profitable in comparison to conventional rope access. Wind farm yield availability is achieved for drone inspections, so higher wind farm yield availability. Then the USP again of using a planner tool like this is the weather uncertainty, which plays a major role or a major factor on real world KPIs, is rightly modeled or approximated, I would say. And lastly, AIRTuB drone with a laser scanner has a great potential for using learning curve in the future. So this is also like a typical graph, what Ludolf mentioned. I definitely see there is a quite, this is quite promising in terms of efficiency, quality, and speed. We are definitely going up. And this will reduce the overall cost when compared to now in future. So a schematic to end with is what I have is like an AIRTuB drone performing the inspection in the future. But this time, the AIRTuB drone being a smaller drone, that is so the inspection could be made possible by using support vessels instead of the large vessels currently being used. And perhaps also like an offshore hub for drone charging in the future could be a solution. So this brings me to the end of the presentation, and I'll be happy to take any questions.
Well, Vinit, thanks a lot. And I understand that you are giving this presentation from the other side of the world. At least that's what I was told. So that makes it even more impressive that you took the time for this. And apparently the technology helps us in, let's say, giving you the floor and having you as a final presenter in our conference on these work packages. Are there questions in the audience or from the audience? Because in fact, you more or less complete, let's say, the story. At least that's what I understood from it, that you in fact say that we are on the proper track with AIRTuB for, let's say, solving this problem. Anyone who wants to add something to it? Apparently you have been very clear. That's my conclusion. Then I think we have to leave it there. But I don't know if you have still some time to stay a little longer with us, because we want to have a kind of, we want to finish this gathering with a kind of panel discussion. And maybe we can, maybe you can join this panel discussion as well from the location where you are. Yeah, okay, that's great.
Certainly, yeah.
That's great. Then I think I'd like to invite all the presenters here on the stage. And then, well, let's try to have some discussion on let's say the findings that we did until now. May I invite the presenters? And then, unfortunately, we haven't got Beatriz online anymore, but I think we are with a big team. There are 2 microphones, so maybe we can use the other one as well. The first statement I would like to make is AIRTuB isn't needed anymore in the future because the designer and the builders of the blade will solve the erosion problem. Who wants to comment this statement?
I think maybe I think it should be a 50-50 in a sense. The research like us, what we've done in the AIRTuB should aid a final goal, like you say. The designers we should provide the tools and the knowledge to help them achieve what you just said.
Okay.
I think it should be both ways. We learn from the industry that the designers' approaches, how beneficial in a sense, also from research and development. So I think it's both ways. It's not a one-way track where that is achievable just by the design process. That's my opinion.
Ludolf, look.
And of course, if there's new technology improving blades, there will also new kind of failures introduced. So talking about the protection of the leading edge, there are some concerns when you put it during the operate and maintain phase. There are some new kind of failures that occur that you also would like to see, to predict and to prevent.
Yeah.
So that's also with technology. You also slightly introducing some new potential failures.
Clear.
So.
You want to add something, Loek or Vinit? Do you have any comments on this statement that what we are developing is not useful in the future anymore?
No, definitely. Like if I could comment as from my last slide, the future is definitely positive, and just joining the pieces from Luke's work where he talks about machine learning. So as we acquire more and more data, it is possible to just go efficient in terms of this methods that we are proposing for the inspection. So definitely there's a bright future for this scope of research.
Okay, thank you. Is there anyone from the audience who wants to put a question to the...
Yes, this AIRTuB drone, is it also, I don't know what it costs, but is it possible that every windmill at sea gets its own drone, so you don't need any boats anymore, you just install the drone at the windmill and it does its work during the lifetime of the windmill? Is that possible?
Well, then you refer to the resident drone, the drone living in the wind farm. I think this is a question that Ludolf can answer because he will have an opinion from the business case that he developed.
Yeah, we took a look at that option because that's very promising because we are facing high logistic costs going with a drone to the park and then fly and then change batteries and yeah. So that's really I think we looked into. To be honest, we didn't look in the cost. What will be the cost of having a kind of hub? Because I expect it will be quite high. And for the autonomous inspection, you need also some sophisticated controller for automatically inspect, and also that will be very costly, I think. But it's the most promising scenario that we'd like to, so we investigated because it's the most promising scenario, having a hub station and fly from there. But yeah, we didn't calculate it, but we took into account the benefits if we had some hub, what would be like the savings in maintenance cost.
And
So
there's, of course, quite some research going on resident equipment in wind farms. And we also know that if we, let's say, create large numbers of this kind of equipment, costs will go down. And that's a part of, let's say, the AIRTuB idea, that if we indeed equip every turbine with its own technology for inspection and repair, this could, let's say, in the end be realizable. I think you also know that Fugro has last year started the RoboDock project, which is also working with a kind of hub, which might be complementary to our developments. But anyhow, Gerard.
Well, I'm still absorbing a little bit your first question.
Okay, you have to cheer.
Because you once made a very nice roadmap for AIRTuB.
Of course.
And that roadmap, if I remember correctly, lasts until 2030.
That's correct.
Are you saying now that there's a need to revisit this roadmap? Or do we still continue the path which you proposed? Because I still think there are still a lot of things to...
It's nice that you refer to the roadmap, and I showed it briefly when we started. But my next statement is based on this roadmap, because that is in 2030, we will have fully autonomous blade inspection and repair functionality in the wind farms. Do you have an opinion on that? Do you think that is realizable?
That's difficult to say. Ferry. These things
you don't have this
very
glass ball.
Risky, we will make a lot of progress into that direction. That's for sure. If it's ambitious, because 2030 is
it's already
8 years
soon
from now. Things go fast. We see a lot about inspection. I'm not sure if we see so much about repair or automatic repair already. And that is, of course, the next step, and it may be more challenging, is my feeling.
We need to work on that.
Inspection is maybe more easy to do than a repair. But I see you want to say something.
Different category 1, 2, and 3. Repairing versus category 4, 5. You still have the big damages that you probably can't repair with a crawler. That's because you have to prepare the surface and sanding and laminating, etc. So it's.
Well, my understanding was that category 4 and 5 develop after category 1, 2, and 3. So if we are able to, let's say, repair before it gets to the level of category 4 and 5, we save on energy loss production, because the higher the category, the more energy loss production we have seen during these presentations. But that means that we have to do regular small repairs. That is part of the AIRTuB roadmap, I think.
Yeah, but you have also lightning strikes for that kind of damages that you, in fact, cannot predict.
That's true.
You have to. You have still some maintenance on that, so different kind of failures. Leading edge, I can imagine, because you are early prediction, and you can plan it more accurately and prevent that it will become 4 and 5. Yeah. But for other
structural defects, that is the part that we, of course, want to do further research into as well. I think there was another question in the audience.
It's working. Actually, I got already some answers, because I was referring to category 4 and 5. The lamination I do understand with AIRTuB, of course, but if you have inside damage, and then compared to rope access, because it looks like it's a competition between rope access and AIRTuB. It seems, but in some cases nowadays, practical-wise, what you see, if you do an inspection, or you need to do an internal inspection, or even ultrasonic inspection, makes the difference. I do believe in the laser technology and the data, for sure, but nowadays there are a lot of problems also with the internal defects, and then is what you see is you go into the sky climbers and you go in a rope access repair. Did you also took that part into your cost model?
Is there anyone? Yeah, maybe Ludolf, you can answer this question, or?
Yeah, probably. But for the structural damages, we have the crawler for detecting with his sensor for structural damages for critical points. You cannot go everywhere with a crawler. So the idea is for the big drone puts the crawler on the blade, and he inspects the critical areas, and then give an indication, okay, are there some structural damages to take into account and to repair. So that's part of AIRTuB 1, and that has influence on the end of life. And in our calculation, we said, okay, there's a beneficial when you use that at more or less at the end of the life of the concession. You do an inspection, you can predict or maybe postpone the end of life, and that's good for the business case. So you can produce a couple of years longer based on a severe, accurate inspection with the crawler, with the sensor for the structural damages. So that's we calculated, but that's.
And then my last question will be, will it also be including with the LPS inspection, the lining protecting system?
I'm not quite sure about that.
Who of the experts can answer this question? No, okay, let's get the microphone back. Thanks. Then I think we are about to going to close this meeting, but I have one more statement I'd like to have your reaction on, and that is, it's not technology development that is, let's say, keeping us from realizing this ambition. It is regulations and matters of law that will keep us from realizing this. What's your opinion on that? Maybe, Loek, do you have an opinion on? You're not a lawyer, I believe. Here, microphone. Oh.
That's a difficult question to ask a software engineer about a wind turbine.
But you are an expert. So.
Software engineer. I live in Vlissingen, so if I take a 10-minute bike ride to the beach, I can actually see the wind farm Borselen out there.
Yeah.
I was opposed to it because it's really ugly. But now it is there, and now I see what it does for us as a region, for the province of Zeeland, but also for renewable energy. In this time, I'm quite happy that it's there, actually. I find it difficult to answer your question directly, but if I take an analogy to software engineering and data science, which is stuff I do know, then I think there should be a bit of regulation and law to not go full cowboy style and do everything without thinking about it. It would be unfortunate if there were casualties, for example, that could easily have been voorkomen. Avoided, thank you. That could be
Great, thanks a lot.
What would I do without you?
But we understand your point, I think.
Yeah.
Yeah. Because now, with the drone flying beyond line of sight is not allowed. And that means if we have a fully autonomous operation with drones and crawlers offshore, quite some regulations need to be modernized and adjusted. But anyhow, Gerard, you want to say something about it?
Not really, but generally speaking, yeah, the energy transition. Well, we are here at Hanze at entrance, and we have here 11. We are with 11 now lecturer professors on energy, so much more than only wind energy. But 2 of them, they work on legal aspects. And if you talk with them, they say the energy transition is only and not so much this drone inspection, but energy transition in general. It's the main problem are legal aspects, and of course we do not agree because we also see a lot of technological challenges. But yeah, generally speaking, I have the idea that regulations can be a showstopper for many things. You also see it now with the how do you call it, the overloading of the grid, a lot of legal. So generally speaking, I think we have to, and at least we have to be careful
to take
it into account.
Yeah, that's clear.
I think that's true. Good point. Yeah.
Wow, that's clear. Vinit, do you want to add something to it? Not for now.
I completely agree with the comments for the past one.
I didn't follow it, but okay. I think then we can go to a closure of this meeting. I'd like to have once more a big hand for the experts. Thanks a lot, and well, I'd like to thank the audience for listening and joining this meeting. Also the online audience. Of course, we will continue with AIRTuB, and this is not the last meeting of presenting the results of AIRTuB, because on the 24th of November we have the final AIRTuB, let's say, gathering or conference. It will take place at NLR in Marknesse, and there we will have some demonstrations with drones and crawlers, and we will gather as much as possible of the results of the whole project together and demonstrate and show it on that event. So please come there as well. You will receive an invitation. Yeah, I think I'd like to thank Hanze and Entrance for hosting us here. It was a very nice place to be. And we will have a drink, and the people online, thanks for joining as well. Thank you.